Need your FastMCP client to handle LLM sampling, requests from servers with custom logic. You'll see how to implement a sampling handler that processes conversation messages, respects server preferences, and returns generated responses, all while maintaining full control over model selection and response formatting. The pattern uses FastMCP's built-in types to cleanly separate message content, sampling parameters, and request context. From FastMCP import client. From FastMCP client sampling import. Sampling message. Sampling params. Request context. Async def sampling handler. Messages, list sampling message. Params, sampling params. Context, request context. SDR. Hash your LLM integration logic here. Hash extract text from messages and generate a response. Return, generated response based on the messages. Client equals client. My MCP server, hi. Sampling handler equals sampling handler. This implements the callback handler pattern for LLM integration, where external systems delegate text generation to your custom logic while maintaining protocol independence. The distinctive aspect is the inversion of control. Instead of your code calling an LLM API directly, the framework calls your handler when sampling is required, abstracting away transport and protocol details. The design follows a clean separation between message processing and generation logic. Your handler receives standardized message objects and parameters, allowing you to focus purely on prompt construction and response generation without managing connection state or protocol specifics. This creates a declarative interface where you define what to generate, not how to coordinate the request cycle. This pattern matters because it decouples your LLM logic from infrastructure concerns. You can swap underlying models, modify prompt strategies, or change response formats without altering the communication layer. It's particularly valuable in distributed systems where you need consistent sampling behavior across multiple clients, or when integrating with different LLM providers behind a unified interface. Let's break it down line by line. From FastMCP import client. This imports the client class from FastMCP, the core interface for connecting to and managing MCP servers. It handles all low-level communication, letting you focus on implementing the business logic in your handlers. From FastMCP client sampling import. This imports FastMCP's sampling utilities, which define the message and parameter schemas for AI model interactions. These types ensure consistent data structure between your handler and the MCP server, preventing runtime validation errors. Sampling message. Sampling message defines the structure for individual messages in an LLM conversation. It standardizes how prompts, system messages, and user inputs are passed to your sampling handler, ensuring consistent processing regardless of the client's origin. Sampling params. Sampling params defines the generation parameters for AI model inference, like temperature, max tokens, and stop sequences. It standardizes how sampling behavior is configured across different model backends, ensuring consistent control over text generation. Request context. Request context provides metadata about the incoming request, including authentication, request IDs, and client information. It enables request-specific handling like logging, access control, and tracing, while keeping your core logic clean. This is the standard pattern for context-aware processing in FastMCP handlers. This closing parenthesis terminates the client instantiation, finalizing the server connection with the specified handler. It's the required syntax to complete object initialization, ensuring all parameters are properly passed to the constructor.
Async-def sampling handler.
This defines an async handler function, required by FastMCP for AI model interactions. The async declaration enables non-blocking execution, critical for handling concurrent requests without thread starvation. All sampling handlers must follow this pattern to integrate with FastMCP's async architecture.
Messages, list sampling message.
This parameter accepts a list of sampling message objects, representing the conversation history or input prompts. Each message contains role and content fields, enabling structured dialogue handling for LLM interactions.
Params, sampling params.
This sampling params parameter contains all generation configuration, like temperature, top P, and max tokens. It lets your handler dynamically adjust the LLM's behavior per request, ensuring consistent control over response characteristics.
Context, request context.
The context, request context parameter provides request-specific metadata and utilities, including logging, cancellation handling, and progress reporting. FastMCP injects this automatically for each call, ensuring your handler has access to execution context without manual setup. This follows the standard pattern where all MCP tool handlers receive this context parameter for consistency.
SDR.
This return type annotation enforces that the sampling handler must return a string. It guarantees the FastMCP server receives a consistent response format, preventing type-related errors in the AI integration pipeline.
Hash your LLM integration logic here. Hash extract text from messages and generate a response. Return generated response based on the messages.
This placeholder marks where you implement your LLM integration logic. The function receives conversation history in messages, generation parameters in params, and must return a string response that the MCP server will forward to the client. The pattern here is AI tool implementation hook. You extract text from messages, process it through your model, and return the generated output. This is the core interface between your LLM and the MCP protocol.
Client equals client.
This instantiates the FastMCP client, the central interface for registering and serving AI callable tools. The client manages the connection lifecycle, handles request routing, and enforces the protocol between your Python code and the MCP server. All tool registration and execution flows through this instance.
My MCP server, Pi.
This specifies the FastMCP server entry point file. The client uses this to locate and connect to your server implementation, enabling message processing and tool execution.
Sampling handler equals sampling handler.
This registers the sampling handler function as the callback for AI model sampling requests. FastMCP routes all text generation calls to this handler, which must return the model's response string. The pattern ensures clean separation between the server infrastructure and your custom LLM logic. This closing parenthesis terminates the client instantiation, finalizing the configuration with the specified sampling handler. Without it, the object creation would be incomplete, causing a syntax error. This pattern ensures all required parameters are properly set before the client starts. FastMCP sampling pattern. The sampling handler callback bridges AI models and client logic, transforming raw messages into structured responses while maintaining protocol flexibility. the client must return a string response, even if your LLM integration uses complex objects internally. This pattern enables seamless LLM integration without coupling your client to specific model providers.
The handler that answers everything knows nothing of the questions it will receive.